Hello my dear students, welcome everyone. Today I am going to deliver lecture on oxidation and reduction of aldehydes and ketones. Now let's start on Clemmensen and Wolff-Kishner reduction. During both Clemmensen and Wolff-Kishner reduction, the carbonyl group of aldehyde and ketone reduces to methylene group, that is we get alkane or hydrocarbon. Both the reactions are same respective to the reactants and products, but the only difference is reagent. During Clemmensen reduction, zinc mercury amalgam and concentrated hydrochloric acid are used. For example, when acetaldehyde is heated with zinc mercury amalgam and concentrated hydrochloric acid, we get ethane. Just follow the technique. Just change the carbonyl group of aldehyde into CH2 group. You can add it CH3. You can write CH3, that is ethane. If you consider example of acetone, just change this keto group into CH2. So acetone will change into propane. So these are Clemmensen reduction. During Wolff-Kishner reduction, just instead of using zinc mercury amalgam and concentrated hydrochloric acid, in Wolff-Kishner reduction the reducing agent is hydrazine and concentrated potassium hydroxide in boiling glycol. Glycol is a solvent. Take a beaker. Take some amount of glycol. Take a test tube. In the test tube, put hydrazine, potassium hydroxide and boiling. Then if you add acetaldehyde or acetone, you will get ethane and propane, similar to that of Clemmensen reduction. So the only change is just change the reagent, that is hydrazine, potassium hydroxide in boiling glycol. You know that hydrazine is used as reducing agent. It has one very important use, that is it is used as rocket propellant. Here also change it, just change it. So you see in both of the reduction, Clemmensen and Wolff-Kishner, the reactant and that of products are same, only the change is reagents. During Wolff-Kishner reduction, the reducing agent is zinc mercury amalgam and concentrated hydrochloric acid, while during Wolff-Kishner reduction, the reducing agent is hydrazine, potassium hydroxide heated in boiling glycol. So I think you understand it. So the next topic is oxidation of aldehyde and ketone. So you see aldehydes easily undergo oxidation in presence of oxidizing agents mainly such as alkaline solution of potassium permanganate, acidified solution of potassium dichromate, nitric acid, these are the good oxidizing agent. In presence of other oxidation agent also, aldehydes oxidizes to carboxylic acids. Why aldehydes easily undergo oxidation? Because the keto carbon is attached to hydrogen atom. See here, this is keto carbon attached to hydrogen atom. That's why aldehydes easily oxidizes to carboxylic acid group. For example, when acetaldehyde undergoes oxidation in presence of any of the oxidizing agent, you get acetic acid, that is the CHO group will change into this, others remain as it is. If you take the example of propanaldehyde, on oxidation it will change into propanoic acid. Just change the this group into COOH group. If you consider benzaldehyde on oxidation in presence of any of the oxidizing agent, will change into benzoic acid. But ketones do not undergo oxidation easily because the keto carbon is not attached to hydrogen atom. But under the presence of very strong oxidizing agent such as concentrated nitric acid, under drastic conditions, high temperature and pressure, ketone oxidizes to a mixture of carboxylic acids, and each acid has lesser number of carbon atoms than that of parent ketones. During the oxidation of symmetrical ketone, no rule is followed, but during the oxidation of unsymmetrical ketone, one very important rule is followed, that is called Popoff's rule. So let's see the oxidation of ketone. So you see, this is symmetrical ketone because the keto group contains same numbers of carbon atoms. During the oxidation of symmetrical ketone, no rule is followed. You can break at any site of keto group, either this or this, because it is a symmetrical ketone. If you break here, so this site contains 2 carbon atoms, write 2 carbon atom carboxylic acid, that is acetic acid. If you consider this only 1 carbon, so write 1 carbon carboxylic acid, that is formic acid. So when acetone undergoes oxidation in presence of concentrated nitric acid, under drastic conditions, you get a mixture of acetic acid and formic acid. See, both of the acid contains lesser number of carbon atoms than that of parent ketone. But for unsymmetrical ketone, the oxidation occurs according to Popoff's rule. POPOFF'. According to Popoff's rule, when unsymmetrical ketone undergoes oxidation, then the smaller alkyl group takes up the keto group. In other sense, you can say the cleavage occurs at this is keto group. This site contains 1 carbon atom, this site contains 2 carbon atoms. The cleavage occurs at the larger carbon sites. So split it. So you get carboxylic acid having 2 carbon atom from this part, and also another carboxylic acid having 2 carbon atoms in this part. So you get a mixture of acetic acid, 2 carbon atom having acid, acetic acid, and here acetic acid. So this is Popov's rule. Clear? So remember it. Aldehydes easily undergo oxidation because the ketocarbon is attached to hydrogen atom, and when any aldehyde undergoes oxidation in presence of any oxidizing agent, good oxidizing agent should be potassium permanganate, dipotassium dichromate, nitric acid, then the aldehyde group, that is CHO, oxidizes to COOH group, that is carboxylic acid group. But ketones do not undergo oxidation. Why? Because there is no hydrogen atom attached to ketocarbon. That's why ketones do not undergo oxidation easily in presence of the common oxidizing agents such as potassium permanganate, potassium dichromate, or nitric acid, that is dilute or concentrate, etc. But ketones undergo oxidation at high temperature and pressure in presence of fuming nitric acid or concentrated nitric acid. There is no rule of oxidation of symmetrical ketone, but for oxidation of unsymmetrical ketone, Popov's rule is followed. During symmetrical ketone, you can break at any side of keto group, so you get a mixture of 2 carboxylic acids. During unsymmetrical ketone, always remember it, the smaller carbon atom takes up the keto group, or you can say the cleavage occurs at the larger carbon site. I think you understand it. So next topics. So let's understand Tollens reagent test. It is the identification test of aliphatic or aromatic aldehydes. Ketones do not give Tollens reagent test. Actually, Tollens reagent is 1:1 ratio of ammoniacal solution of silver nitrate. That is, you can say it is equimolar mixture of ammonium hydroxide and silver nitrate. Tollens reagent acts as oxidizing agent, and it oxidizes aliphatic or aromatic aldehydes into corresponding carboxylic acids. As Tollens reagent is a weak oxidizing agent, thus it cannot oxidize ketones. You know that any oxidizing agent itself it is reduced. Hence, Tollens reagent reduces to metallic silver. Whenever you add any aldehydes, aliphatic or aromatic, along with Tollens reagent, heat in indirect way. Take a beaker, take water and heat it. Then after some times you see that silver metal is deposited at the bottom of the test tube. As the silver is shining like a mirror, that's why Tollens reagent is also called silver mirror test. See it. When you mixed ammonium hydroxide and silver nitrate, that is, it is a composition of Tollens reagent in 1:1 ratio, they react and give this complex. This is called Tollens complex. Actually, this Tollens complex is responsible to carry out the oxidation of aliphatic and aromatic aldehydes to carboxylic acid. Thus, Tollens reagent acts as oxidizing agent and itself it is reduced to metallic silver. As the deposited silver is shining like a mirror, so Tollens test is known as silver mirror test. Ketones do not give this Tollens reagent test as it is a weak oxidizing agent and it cannot oxidize ketones. In chemistry, there are lots of exceptional cases. Listen and see the reaction. Among all the carboxylic acids, it is the formic acid which responds to Tollens reagent test. I repeat, it is the formic acid only among all the carboxylic acids which undergoes Tollens reagent test. Other compounds, yes, there are other compounds, that is glucose. You know that glucose contains one aldehyde group, so glucose also undergoes Tollens reagent test. So you see, both glucose and fructose undergo Tollens reagent test. You know that glucose has aldehyde group, so it easily undergoes Tollens reagent test. But fructose has no aldehyde group. It has only ketone group. But as Tollens reagent is an alkaline medium, that is ammonium hydroxide is present, thus fructose undergoes rearrangement to form aldehyde, which gives the Tollens reagent test. And the rearrangement is called Lowry D. Brown Van Eykenstein rearrangement. So see, both glucose and fructose give Tollens reagent test. Fructose has keto group, but it undergoes rearrangement in alkaline medium. Alkaline medium means in Tollens reagent you have taken ammonium hydroxide, which provides alkaline medium in the reaction. The rearrangement is called Lowry D. Brown Van Eykenstein rearrangement. See the rearrangement. This is the structure of fructose. Okay, this is the structure of fructose. The two hydrogen atoms shift here. So in upper part you get aldehyde group and the next carbon becomes CHOH. Shift one hydrogen, shift other. Due to the presence of this aldehyde group, actually fructose gives a positive Tollens reagent test. So let's understand the reactions involving during Tollens reagent test. Aldehydes oxidizes to carboxylic acid, but as the reaction takes place in presence of ammonium hydroxide, and as ammonium hydroxide is basic in nature, so you know that acid and base never coexist. Hence they react together to form ammonium salt of carboxylic acid. I have taken example of acetaldehyde. Any aliphatic or aromatic aldehyde undergoes Tollens reagent. This is Tollens complex. You know that this is Tollens complex. You have already taken ammonium hydroxide, they react together. The aldehyde oxidizes to carboxylic acid at first, which reacts with ammonium hydroxide, and finally we get ammonium acetate. Silver metal is deposited at the bottom of the test tube. The byproducts are these. Similarly, benzaldehyde will change into benzoic acid at first, which combines with ammonium ion to form ammonium benzoate. Now, the very important question for entrance. Now, tell me, what is the oxidation state of silver in Tollens complex? So tell me, this is Tollens complex. What is the oxidation state of silver in Tollens complex? Oxidation state is X. So oxidation state of silver in Tollens complex is, set is X. X plus 2 into ammonia has always oxidation state 0, plus which any hydroxide ion has oxidation state -1. You know that whenever you dissociate sodium hydroxide, sodium positive 1, OH negative 1, so always negative. And do you know what is the rule to find the oxidation state? For neutral compound, it's a neutral because no charge is there. For neutral compound, the sum of oxidation state is always equal to 0. Therefore, X equals to +1. So, the oxidation state of silver in Tollens complex is +1. And you know that Tollens complex reduces to metallic silver, and as the silver is in elemental state, and you know that in any elemental state the oxidation state is always 0. So remember it, during Tollens reagent test the oxidation state of silver changes from +1 to 0. So during, this is the very important, during Tollens reagent test the oxidation state of silver metal changes from +1 to 0. That's the very important for entrance, okay? Very important for entrance. Now, let's start another identification test, that is Fehling solution test. Fehling solution test also an identification test. So, please understand the Fehling solution test of aliphatic aldehydes. Actually, Fehling solution is a mixture of two solutions containing Fehling's A and Fehling's B. Fehling's A is aqueous solution of copper sulfate, and Fehling's B, this is the entrance question, okay? Fehling's B is alkaline solution of sodium potassium tartarate. Tartarate comes from tartaric acid. You know that tartaric acid is present in tamarind. In tamarind, tartaric acid is present. Its sodium and potassium salt is called sodium potassium tartarate, which also called Rosyl salt. So, Fehling solution is an equivalent mixture of Fehling's A and Fehling's B. Fehling's solution acts as oxidizing agent, but it is weaker oxidizing agent than Tollens reagent. You know that Tollens reagent oxidizes both aliphatic and aromatic aldehydes to corresponding carboxylic acids, but Tollens reagent oxidizes only aliphatic aldehydes, not aromatic aldehydes. So, during Tollens reagent test, what happens? You know that Tollens reagent acts as oxidizing agent, so it reduces to cuprous oxide Cu2O, which has red precipitate. So from the color we can identify the aldehydes. So once again, Tollens reagent is an equimolar mixture of phalanx A and phalanx B. Phalanx A is aqueous solution of copper sulfate and phalanx B is alkaline solution of sodium potassium tartrate, that is rosyl salt. Whenever you mixed it, you get the phalanx solution. Only aliphatic aldehyde gives phalanx solution taste. Aromatic aldehydes do not give because phalanx solution is weaker than Tollens reagent taste. Ketones do not give this taste, but both glucose and fructose respond to this taste. Okay, so understand what is the reaction during phalanx solution test. Actually, during phalanx solution, copper hydroxide is formed as reaction intermediate, which is actually responsible to oxidize the aliphatic aldehydes to corresponding carboxylic acid. So example, acetaldehyde when reacts with Tollens phalanx solution, it gives copper hydroxide. As the reaction takes place in presence of alkaline medium, sodium or potassium hydroxide reacts. This aldehyde oxidizes to carboxylic acid. Understand at first, CH3COOH. Acetic acid is formed, but you know that in a solution, acid and base never coexist. That's why this acid reacts with this sodium hydroxide to form sodium salt. So it is sodium acetate plus a red precipitate of cuprous oxide. Red precipitate of cuprous oxide is formed along with some molecules of water. This is the complete reaction. Benzaldehyde does not undergo this test. Only any aliphatic aldehydes, okay? Any aliphatic, it may be formaldehyde, it may be acetaldehyde, it may be propanaldehyde. Remember it. So, you learn that aldehydes and ketones undergo oxidation in presence of Tollens reagent, phalanx solution, that is Tollens reagent oxidizes both aliphatic and aromatic aldehyde. Ketones, no. Phalanx solution is weaker than Tollens reagent, so it oxidizes only aliphatic aldehydes, no benzene. Both glucose and fructose are oxidized by Tollens as well as phalanx. Among all the carboxylic acids, formic acid responds to both Tollens reagent test and phalanx solution test. Ketones do not undergo oxidation in presence of toluenes or phthalings because they are much more weaker than usual oxidizing agents such as potassium dichromate, potassium permanganate or nitric acid. You know that though potassium dichromate, potassium permanganate and nitric acid are strong oxidizing agent in organic chemistry, but they cannot oxidize ketone. Ketones undergo oxidation only in presence of concentrated nitric acid or fuming nitric acid under very special conditions, high temperature and pressure. Another reaction is very important for board as well as entrance, that is called iodoform test. So please watch my next video on iodoform test, and I think one question will surely come in your forthcoming term 2 board exam, whether it is cbse, isc or wbb, as well as in entrance, JEE Mains or NEET. So please watch my next video on iodoform test.